We recently put out a call asking our viewers to submit some attempts at step questions so that I can mark them and discuss issues of presentation. I've selected 3, which are going to feature in a series of 3 videos. These questions have not necessarily been selected because they're the strongest or the weakest, but rather because they provide nice examples of certain key points surrounding presentation, which I'd like to explain. If your work does not feature in this series, I'll nonetheless be in touch with your marked script and some feedback. In this first video, we're going to look at a piece of work which has a really good handle on the underlying mathematics, but loses quite a few marks due to small issues of presentation. We'll think carefully about how we could avoid these pitfalls. Before we turn to the actual content of the solution, I just want to make a very quick point about presentation. This is a multi-part question. The question itself is broken down into parts 1, 2, 3, and 4. In this solution, the student hasn't written, for example, part 1, part 2, part 3, to tell the reader where one part ends and the next part begins. Now, this would not be deliberately penalised. However, it substantially increases the risk of an unfavourable marking error. For instance, if you get a bit lost in your workings and there comes a point where the examiner decides, I'm not sure what this student's doing, I'm not sure they know either, I'm not going to exert an infinite amount of energy trying to understand something that's not making much sense, there will come a point sometimes when they make such a decision. If you haven't marked where the next part begins, it's much harder for them to know when they're supposed to jump back in and perhaps find some more method marks that you can be awarded. They're not going to go to enormous lengths to disentangle your work if you've made it difficult to follow. So it's such an easy thing you can do just to keep the examiner on your side and reduce the risk of errors. With that said, let's jump in. So in the first part of the question, we're trying to prove a result about a product by induction. The student has begun with the base case, which I think is entirely reasonable. You will notice on the mark scheme, the base case is for the B mark, the third mark on the paper. Whereas the way we're normally taught to set out induction, for example, in school, is that you do the base case first. There's nothing wrong with it being out of order, and here this B mark is definitely received. The base case is being handled entirely convincingly here. But if you want to try to follow the mark scheme in order, again, just to reduce the risk of an unfavourable marking error, you might choose to do the base case after the inductive step, because that's what they tend to do. In terms of this logic here, the only thing I'd say is, 1, I'm not a big fan of working along the page when all you're doing is processing the same expression. So to me, if I see something equals something on one line, that means they're 2 sides of an equation, and the fact that these 2 different things are the same is the interesting mathematical statement. What's going on here is not that we have 2 things that are interestingly equal. We've got one thing, and we're just processing it one step at a time. So when you're processing an expression, I would try to work down the page just to make it slightly clearer what you're actually asserting. The other thing is, it maybe wouldn't have hurt to say something like double angle formula there, obviously the hyperbolic version, although I really like how the student's written a line, or a step, where it's 2 times x over 2, which is really as good as saying that the double angle formula has been applied. So we definitely get that B mark, B being an independent mark. Next, the student very nicely makes the statement of the inductive hypothesis. They're supposing that result holds for n equals k, so we definitely get that E explanation mark, the first one on the paper. Now, if you look at the mark scheme, there's only one mark, one M method mark, for the entirety of the inductive step. If there's only one mark for a large amount of working, it can sometimes be unfavourable towards students, because the smallest slip can then cost you all your credit for that section. So let's look at what the student's done here. They've written down the n equals k plus 1 case. I would like to see, ideally, something like consider, or now we have, or some sort of thing in words, putting this equation or this expression into context. Otherwise, it's not really clear where this line has come from. It's as if it's just appeared out of thin air. Is it something separate that we're considering? Well, yes. Or is it something that is supposed to follow algebraically from the line above? Here, it's completely obvious from the context that this is the n equals k plus 1 case that we're considering. So there's no danger of losing a mark for this, but it would make it easier to follow and reduce the risk more generally. Just to put this in context, something like, now consider n equals k plus 1. It's always nice to say where equations come from. Now, what's the student actually done? They've written this in an interesting way, where they've essentially multiplied and divided by that shine in order to force, as the numerator of that fraction, the thing that we inductively assumed to actually show up. Now, one thing I would have liked ideally is to make it slightly clearer that the inductive hypothesis is being used in going from here to here. So clearly this thing is being rewritten using our assumption. Although the student has clearly done that, it would be nice to say in words. For example, when you make the inductive assumption, you could call that equation equation 1 or equation star and then say by star. As a general rule, if you're going to apply a result from earlier in the question, you want to be very clear that you're being completely explicit about how it's being applied. I wouldn't deduct a mark for this here because I think from the context it's reasonably clear. However, I am unfortunately going to have to deduct the M mark due to the fact that in this step, a denominator of shine has been introduced. In the original expression, this is valid for all x, all of the x that we could possibly care to imagine. Whereas here, this is only valid if the shine is non-zero. Now you'll notice there's a line on the mark scheme, which is legitimate because x is not 0 and hence the shine is non-zero. Without making that point, this expression is potentially invalid for some values, whereas the original was not. So if you're introducing a denominator, you need to make sure to justify that the denominator you've introduced is non-zero. So we do lose a mark there. Now, I agree this is rather harsh. I can say I marked this question for real in 2022, so I do know for a fact that this is where the line is drawn. In another question, you might get away with it, but the reason they're so harsh here, really, is because ultimately introducing that division is the only substantive step in the algebra that we've actually done. Otherwise, the inductive step basically follows immediately from the inductive assumption. So if they're not asking us to do much, then they're going to hold us to quite high standards in doing it properly. So other than that, the inductive step would be fine, but sadly we do lose that 1 mark. The inductive conclusion is then made very nicely. There's not actually a mark awarded in this question for the inductive conclusion, although it's always good to write it because it potentially could be something that's credited. Then we come to the subsequent part where we essentially need to rewrite the result we've just obtained. So again, I'd like when we state this something like now we know, just to put that equation in context, right? It's not just appearing out of thin air, we're recalling something from later. But we need to try and rewrite this in a particular way. The student does this very nicely. So they take what we know, they do a division, I suppose, to try and isolate the coches. It would be nice to have something like an implication arrow here, just to make clear that this isn't some different equation we're recalling. It's actually following from algebra on the above. And then, they essentially introduce an x and an over x, splitting up the product to get it in the right form. So this looks really good, but unfortunately, for the same reason as earlier, we lose this final E mark in part 1 because they have not justified, again, that because x is non-zero, neither this nor this are 0. So actually 2 marks, unfortunately, here have been lost out of 4 so far for something as simple as not justifying the division. So do be really careful with this. We then come to part 2, although unfortunately the student doesn't tell us that, but let's add that in ourselves. So we come to part 2. We write down the Maclaurin series, which is given to us. Not really necessary to put that on the page because it's given to us in the question. So we could have just subbed it into what we're considering and it would have been obvious what we were doing. But we take the expression that we're considering. We plug in the Maclaurin series for the shine. We cancel a y. Now, okay, you could put y not 0 there just to be safe. But I'm not as worried about it here because in the context of what we're doing, we're considering a limit as y tends to 0. Even the original expression was actually invalid for y equals 0. That's the whole point of the limit. The point of the limit is that we're thinking about a y which is close to 0, but not actually equal to 0. So unlike in the earlier offences, not justifying that y is non-zero when I cancel a y, I don't think is an issue here. In the context of what we're doing, the meaning is clear. Reasonable decision to then expand the sum out explicitly just for a bit of extra clarity, and we get that these terms go to 0. So I think that's completely fine. We definitely get the E mark for part 2. And then there's another thing we have to do in part 2, which is, of course, to then reason about essentially what happens to the product as n tends to infinity. So as we're aiming for this infinite version of the product. So it's quite clear what's happened here. The students made a nice, obvious claim that this part of the expression tends to 1 as n tends to infinity. So I think it could be clearer exactly how the earlier result is being applied. I'm not going to deduct a mark for this, but it could be clearer exactly how the earlier result's being applied. In particular, the idea is I'm identifying this thing with the y in the language of the last part, and as n tends to infinity, the y goes to 0. So I think, we definitely get benefit of the doubt here because it is clear enough what's being done. But let me just again make the point that whenever you're using something from earlier, you want to try and be as explicit as possible about how. But in any case, we have this thing, we factored off this piece that we said goes to 1, and then we have the infinite product. So I think that's absolutely fine, and we do access the second mark for part 2. So we now come to part 3. So if we look at the mark scheme, the first M mark actually requires us to do several things. It requires us to compute the shine, cosh of x by 2, and cosh of x by 4, even though the question only initially asks us to do cosh of x by 2. So this is something that's not all that surprising. They don't want to give away marks too lightly, so even if the question's only asked us to do one thing, if it's essential for the subsequent calculation that we do some other things too, and clearly plugging x equals ln2 into this identity means we'll need to figure out some other trig or hyperbolic functions at that value of x. If there are other things they're going to have to do, they might bundle it into the same mark. So quickly looking here, we've managed to obtain the cosh, we've managed to obtain the shine, and we've also managed to obtain the other cosh of x by 4. On the mark scheme line, they write it in rooty notation. Here we've got exponent notation. That's not a problem. It's just two different ways of writing the same thing. So certainly we access this method mark. So subsequently, we're plugging this into the identity from earlier. Now, it's reasonably obvious that that's what the student has done here, but it would be nice to say that. Plugging x equals ln2 into earlier equation, maybe giving the equation a name, just so that this doesn't appear out of thin air. Otherwise, even though it's very easy to do, the reader is having to figure out what it is you're doing. And there's only so much effort that the marker will put into that. So if everything's proceeding smoothly, it might be obvious enough and you'll get away with it. But in the event that you're doing something slightly wrong and the reader gets confused, there comes a point where they'll lose their patience. So always try to justify where equations are coming from. Now we have a bit of a problem here. So the student has very convincingly reasoned through what the x by 2 and the x by 4 coshes are. They have just assumed that cosh of x by 8 is as given here. Unfortunately, if you look at the actual statement of the question, even though, of course, yes, there is eventually a ... because we're not going to process every single term in the infinite product explicitly, they did go up to x by 8 explicitly. If you're going to do a sort of ... for a result that is infinite, an infinite product, an infinite sum, it's really important to make sure that you are at least going as far as the question does in terms of how many terms are handled explicitly. So we can definitely get the M mark here for the fact that, although they didn't say as such explicitly, it's obvious that they have attempted to plug x equals ln2 into the given result. But we have to deduct an A mark because they didn't explicitly demonstrate that this is the term. It looks like too much of a bluff. They could just be reading this from the text of the question. So you have to go to the same level of detail that they do. Subsequently, there's then an A mark for having done, I suppose, really just some more simplification. So really the M and the A here, they're the M and A together on the mark scheme from plugging in. But you see they've gone straight to the processed form, not the direct form that that they have given on the mark scheme. In the subsequent A mark, what has really happened is that they've rearranged this to make 1 over ln 2 the subject. So I'm reasonably satisfied that that's happened. So they've clearly pulled out a bunch of 2's, and they've clearly used the laws of exponents to collect, you know, this one and this one and this one. They've kept track of all the factors, and given that there is a 3, 4, 3, 4 there, it's clear there's no bluffing going on. There are no factors going mysteriously missing. So I think this second A mark we can award. As for the E mark, so the E mark here is clearly associated to the handling of the geometric series. Because they have actually bunched it together as an explicit geometric series, and then they've written that 2 to the 1, it's sufficiently clear they've used the geometric series formula. We can award this mark. What you mustn't do is go straight from there to having evaluated it without ever having written it in a form that makes clear you are dealing with a geometric series. What would be even better would be to either write the words geometric series or write, you know, this is 1 over 2 squared, this is 1 over 2 cubed, just to make that slightly more obvious that that's what you're doing. But I think this is a sufficient level of detail, and so we can also receive that E mark. So at this point, we've managed to obtain the desired result, and we get the E mark for that justification. Now we come to part 4. So in part 4, we need to derive a very similar looking thing, but to do with square roots, or pies rather, whereas previously we were looking at things that involved a ln, say. So the student has clearly had the right idea here, in that having identified this identity to do with hyperbolics, and then plugged a good value, x equals ln 2 in, we could just as well try to derive a trigonometric analogue, and then plug a good value, maybe related to pi, into there. So they've had the right idea. However, this use of Osborne's rule cannot be credited whatsoever. It is possible by making an imaginary substitution, for example, to properly convert hyperbolic and trigonometric expressions between each other. Osborne's rule is really just the consequence of doing that. But the issue with Osborne's rule is a statement about identities which are purely trigonometric or purely hyperbolic. Our identity features a naked x on the denominator that is neither inside a trig nor a hyperbolic function, and therefore, strictly speaking, Osborne's rule doesn't apply. If you're going to apply clever off-syllabus knowledge like Osborne's rule, you need to be really careful to make sure you're doing so in a valid way. So I respect what the students tried to do here. They've tried to save the work of having to go back through all the earlier steps with the trig version. That would be one way you could do it. You could go back through the entire rest of the question using trig rather than hyperbolics. They've realized that we can somehow convert the hyperbolic to trig, but you'd need to do that by doing something like replacing x with ix and using the relation between sine and cosh for imaginary numbers to sine and cos. It's not enough to just invoke Osborne's rule. Even though it gives the right answer, it strictly speaking doesn't apply. So the only thing I'm then thinking is whether the student could maybe receive a method mark for the fact that they've suggested something like pi by 4 in the trigonometric version of the result. Maybe that could receive a method mark. You'll notice that they do have a method mark allocated at the bottom for the more direct approach, where they say x is pi by 2, or in the hyperbolics where they try the I pi by 2. I'm going to say that since it's not quite the right substitution, and because it's not really, they're only talking about doing it in a result that's not properly derived, I'm going to withhold that method mark, although I do think it's possible that the mark would be awarded. So let's tally up. It looks like the student ran out of time at that point. So we got 1, 2, 3, 4, 5, 6, 7, 8. 8 marks out of 20. So this is a perfectly respectable attempt. 8 out of 20 is not too far off where you need to be getting on average to secure a grade 1. But there are loads of marks that we could have accessed here if we were slightly more detailed with presentation. Things like justifying divisions a bit more carefully. Overall, this was good quality work. The student clearly has a very good understanding. not only of the underlying mathematical context, but also of the big idea behind the question, and what the question setter actually intends for us to do. Unfortunately, the mark awarded doesn't really do justice to the quality of the work, because small presentation issues have stacked up and chipped away at the total. It's so important to remember that if you do anything beyond simple algebraic rearrangement of the line above, you must include brief written remarks, justifying your steps, explaining what you're doing, and putting arguments in the context of the broader problem. Next time, we'll look at another example which suffers from the opposite issue, writing a little bit more than is needed, and therefore running the risk of wasting time. Do remember to subscribe, and thanks for watching.